Hello, I'm Danil, and I'm going to present our work with my colleagues Mikkel, Jakob, and Bas on extracting smart contracts tested to verify Annenkov. This work is motivated by smart contracts, and I'll tell briefly what they are. So smart contracts, for the purpose of this presentation, can be thought as programs in general purpose languages running on blockchain, meaning that all the particularities are coming from the environment where they run. And a blockchain, you can think of it as some fancy replicated database, and smart contracts are stored procedures for such a database. But what makes them so special? Why we want to verify them? So by design, they are for managing money, meaning that typical applications include auctions, crowdfunding campaigns, multi-signature wallets, and so on. And smart contracts after deployment are immutable, meaning even though there is a bug in your contract, you can't really modify the code anymore. And according to coder's law principle, code of your contract is its intended meaning. So that means if there is a bug there, then it also can be considered as part of its meaning. And contracts are interacting entities, so they can call each other, and they can call contracts deployed by any other user, so potentially containing some malicious code. It's a well-known fact that even small flaws in smart contracts can lead to huge financial losses. We'll focus our attention on the functional smart contract languages, and this paradigm becomes more common in modern blockchain implementations. And according to this paradigm, contracts are partial state transition functions, roughly with the following signature. So contract takes a call context, which contains information about the current call, maybe some information about blockchain, and a message on which it can dispatch on old state, and returns a new state and list of actions. And a special piece of software called a scheduler takes care of updating the state and handles transfers from the list of actions and calls to other contracts. And there are multiple examples of such languages nowadays, and just some of them. For example, Lego, the family of languages on Tezos, Liquidity on Doom, Still on Zilliqa, and Sophia on Eternity, and so on. So it's clear that smart contract verification is crucial, and COC is well suited specifically and for smart contract languages, and because we can implement smart contracts as functions in COC, since COC basically is a dependent type functional language. And we want to do all our development in COC and verification as well, and for this purpose we actually do have a concert framework which we presented last year on CPP, but how we can go further with this development. So we actually want to deploy and execute this code on the blockchain. How we can obtain the executable code, and there is an answer to this, and it's called code extraction. So what is code extraction? I think code extraction is a little bit COC specific term, but in general it means it's translation, compilation, or code generation from your formal development in the proof assistant to one of the target languages. And the target languages usually are functional languages. And similar functionality is available in several proof assistants, of course including COC. Specifically in COC, current extraction supports such targets as OCaml, Haskell, and Scheme. And the general idea of extraction is to turn computationally irrelevant bits into a box, and then proofs given by propositions and types appearing in terms will become boxes. The underlying theory of a current implementation is given in a PhD thesis by Pierre Ledouze. But unfortunately, we cannot just take and use the current extraction of COC, obviously, because there are too few target languages which are supported, and moreover, current COC extraction is not verified. But the good news is that there is a MetaCOC project which contains as part of it a verified erasure procedure that corresponds to this idea of erasing irrelevant part to boxes. And so MetaCOC project it's a is an effort of formalizing COC and COC, and it consists of several sub-projects. And here are some projects relevant for us, sub-projects relevant for us. Template COC adds metaprogramming facilities to COC, and in fact it reflects COC's kernel representation and provides quote and unquote functionality. MetaCOC also formalizes meta theory of COC. So the meta theory of COC is calculus of inductive constructions, in particular flavor of calculus of inductive constructions, called predicative cumulative calculus of inductive constructions, or PQIC for short. And also it formalizes safe checker, and finally it formalizes erasure procedure, which is sort of the most important for our work. So what is verified erasure of MetaCOC? So formally, erasure is given as a translation from PQIC, which is a calculus flavor of calculus of inductive constructions, underlying theory of COC, and it translates to lambda box, which is untyped lambda calculus with additional constant box. MetaCOC also provides a proof that evaluation of the original and erased terms agree. For practical bits, for practical use, there are some missing bits. For example, since we want to target type languages, we want also to somehow translate COC types to target language types. And we would like to have more optimizations that would aid sort of remapping and integrating the extracted code to target language code base. So therefore, we contribute with this work, first of all, with implementation of several real-world smart contracts, with testing framework for smart contracts for preliminary bug discovery, allowing to discover bugs early, and with code extraction that allows to generate executable code, sort of to bridge the gap between the formal development of smart contract and the proof assistant and the actual executable code which can run on blockchain. And also our development of code extraction is more general than smart contract languages, and can be applied to various targets. So let me guide you through the pipeline, starting from the development of smart contract in COC and all the way to executable code in target language. So all the things in green here is our contributions, and transformations which are marked with star are verified. So we start in concert, and we can define our smart contract as COC functions here, and after that we can test and verify them using the infrastructure provided by concert, and afterwards we can quote our smart contract using MetaCOC facilities for metaprogramming and get a CIC term, terms in calculus of constructions, and then we can apply a erasure procedure given by MetaCOC and extract types with the procedure we implement in our development. Afterwards, we can optimize the extracted code, which is now is represented in lambda box with additional data structures for carrying extracted types, and from lambda box we can print the extracted code into one of the target languages, and languages given in red are smart contract languages, and languages given in black here are general purpose languages. So Elm is functional language, and Rust contains a well-defined functional subset. We also integrate our development to a verified compiler for COC called CertiCOC, since one of the intermediate representations of CertiCOC is lambda box. And the trusted computing base is the usual of COC, and MetaCOC quote, and of course printing and target language runtime. So our extraction procedure extends MetaCOC with extraction of types and inductive definitions, which is crucial because we target type languages, and also it extended with a verified optimization procedure that removes unused arguments of functions, and logical arguments of constructors. And on top of that, we implement also in Coq pretty printers that generate code in several target languages. So since we consider new target languages, we hit new challenges. So for example, many languages which we consider don't have any unsafe features, and they are required since Coq has a more powerful type system, and the extracted code has to fit to less powerful type system of a target language. And sometimes one has to use some unsafe features to convince type checker that code is actually okay. Many smart contract languages don't have recursive data types, and support for recursion is also limited. So this has some consequences for the extracted code. For example, extracted code not always will be well typed, which is already the case for the standard extraction. But in the standard extraction in OCaml, say, one always can use object magic to make the type checker happy, and we don't have such an option in many our target languages. And limited support for data types and the recursive functions means that, for example, if you want to extract functions in lists, you have to say that your lists are exactly a primitive lists provided by a language, and the functions or Coq lists are exactly the primitive functions and lists in the target language as well. So this is similar to extract inline constant functionality of the standard extraction. Let us motivate a little bit optimizations that we perform. So let's consider a square function which basically takes a list of natural numbers and maps function x times x to each element. If you look at the body of this function with all the implicit parameters made explicit, the map is actually applied. The first arguments to map are actually two types, and this is because how polymorphic functions, polymorphic definitions work in Coq. They explicitly apply to types. And after extraction, these types, of course, become boxes because they are relevant for computation. And naturally, we want to have something with these boxes removed. That would be something what we would like to have. So filter out these boxes and just left with this. And the same goes for constructors such as pair, for example. The first two arguments would be boxes, and we want to filter them out, and because that really simplifies, for example, extracting it to our target languages, and especially remapping. So therefore such a procedure would help solving at least two problems. It would remove redundant computations, obviously, because there will be less applications, and also it would facilitate remapping of language polymorphic functions to target language polymorphic functions. And the same goes for remapping constructors as well. Therefore, we called such a procedure that filters out some boxes. We call it deboxing, for removing boxes. But sort of how we can remove these boxes and why it's safe. So if we unfold a constant, so after unfolding the constant would have a form of some kind of lambda abstraction, and if this abstraction is applied to some term v, and we know that x never occurs free in t, then assuming that the application is actually terminating, it is equivalent to just the body of this abstraction. And the deboxing is a special case of this equivalence, meaning, for example, if we have a function similar to the one I showed before with the polymorphic types, so the type A will never occur, never used in T, and therefore we can safely simplify this expression, leaving us just with one lambda abstraction instead of two. And for constructors, boxes just don't carry any useful information. That's why they can be safely removed. And So that's why we removed boxes from applications of constant. I can remove boxes from applications and of constant and constructors. As I mentioned before, it's basically this deboxing thing is an instance of more general procedure, which we call dearguing optimization for removing dead arguments. For example, for this simple definition foo, it's clear that two arguments m and k are not used. That's why we can simply optimize it to an identity function. So the dearguing consists of two stages. The first stage is analysis, and we generate masks for constant and constructors. In this case, the mask could have the following shape, depending on whether arguments are used or not. And the second stage is using these masks to actually remove the arguments and adjust all the usage sites. But there are some caveats. For example, if a constant or constructor is not applied enough, we had to iter expand it, and strictly speaking, with iter expansion, it might be not an optimization. But in many cases, we actually don't need to iter expand anything, especially if we extract polymorphic definitions. So these definitions are usually applied to all the types. That's why the iter expansion is not necessary. So we proved the following soundness theorems for our development. So we prove soundness with respect to dynamic semantics, which is given by a big step called by value evaluation relation. The first theorem is soundness of dearguing transformation. So if we start with a lambda box environment, sigma and turn t, which are iter expanded according to provided masks, and t evaluates to some value v, that implies that optimized version of t evaluates to an optimized version of v in optimized environment sigma. And then we put all the pieces together, meaning both extraction, so erasure and optimizations, and we start, so we prove soundness of extraction theorem, meaning we start with a constant c in environment sigma, and it's a CIC constant, so it's like, you can think of it as a Coq term. And if it evaluates to a constructor, say true, then after erasure, this erased constant will evaluate to the same constant, to the same constructor true. For the soundness of dearguing, we get this premise that t is iter expanded according to provided masks, and all in sigma is expanded also in a certifying way, meaning that we have a non-certified procedure that performs iter expansion, and then we generate a proof that the expanded version corresponds to the original one. So let's discuss a bit. So what is how I can implement box in target language. So the natural choice would be some data type with one constructor, because box does not carry any computational meaning. But unfortunately, it doesn't quite work because of some semantic discrepancies. So for example, there is this rule. So if some term t1 that evaluates to a box is applied to something, then the whole application of t1 to t2 should evaluate to a box, meaning that something that evaluates to a box is like an argument consuming function that evaluates to itself. So obviously not always possible to express in our target languages. So we still have to stick to unit. But good news is that unit does not really come up that often, and correctness won't be compromised anyway, because even though we hit such a case, then extracted code won't be well typed. Another rule is pattern matching on a box, but recent optimization in Metacoq actually allows to identify all these cases and remove them. So it is also integrated in our development. Therefore, we have the following guarantees given the trusted computing base. So if extracted program type checks, then it gives the same result as the original after evaluation. Let us consider a simple example, a counter contract, and the contract in functional programming is functional smart contract languages. Contracts are just functions, so that's why our counter is a function that dispatches on a message that could be increment or decrement and takes a storage, which is just an integer, and produces new storage. After validating the input, it calls main functionality given by two functions, and here is an example of one of these functions. It's in counter, it takes a current storage and a positive increment, and positive is encoded using refinement types, which are implemented in COC using dependent pairs, meaning the first component is an integer number and the second component is proof that it's positive. So in counter takes a storage, a positive increment, and returns a new storage and a proof that the old storage is actually smaller than new storage. That means that we encoded basically functional correctness of our inc function in its type. Let's see how the example extracts. So we use Elm programming language for showing the example. I think this is one of our target languages that might be the most familiar to you. So the counter function signature basically remains the same. There is no surprises here. So it takes a message, and the message type extracts to a variant type as two constructors, and the storage is just an alias for an integer. The interesting things happen here, and remember our inc counter function was using a positive type for represent positive increments, and now positive type becomes just a simple wrapper around the integer number, and sig, which corresponds to a dependent pair type, now not actually a pair but a simple wrapper around a value. And projection from a dependent pair becomes just a unboxing of a value essentially. So all the logical bits are erased and there are no traces of proofs left here, and moreover our optimization procedure removes all the redundant boxes here, leaving us just with a quite readable code. As a benchmark for our extraction, we implemented several smart contracts, including various versions of a counter contract, of a crowdfunding contract, which is widely used in various tutorials, and by itself it's quite a common use case. I also implemented a prototype DSL interpreter on top of the languages implemented in blockchain, and an escrow contract. We also tested our extraction to Elm, giving it as an input functions with more dependent types, for example featuring something using false elimination, or functions defined by well-founded recursion. I found out that liquidity in Common League in fact has many restrictions, as we already mentioned, and requires more remapping than other languages, but despite these limitations they're still suitable for defining for developing smart contracts. But on the other hand, Elm is closer to Lambda box, and extraction, or rather pre-printing here stage, is more principled. We also implemented a extraction to Rust, which is a very interesting language, and there is we didn't describe this extraction in our paper, and we plan to do a follow-up publication on this. And for now we do have this extraction, and we benchmarked it on some examples from Stylent library, and also simple examples with dependent types, and working on more on bigger examples, including examples from CertiCog benchmark. Let's jump to another our contribution, which is a testing framework for smart contracts. So our testing framework is based on QuickCheck, which is a property-based testing framework for COC, and it's inspired by QuickCheck, a testing framework for Haskell. And the idea is that user can specify properties, and the framework will generate many random tests for testing these properties. And so we follow the same idea and provide generators, and the user can provide generators for our contracts. And the real interesting feature is this bit. we provide a blockchain trace generator that allows to test our contracts not just as functions in COC, but as real sort of interacting entities which can send messages to each other, giving access to testing interacting smart contracts. That gives us overall a cost-effective semi-automated approach to discover bugs, and it aids verification effort, since your verification efforts won't be wasted if you can discover some bugs earlier, so you don't have to actually try proving properties that don't hold. And so this is the first development that supports testing on execution traces, giving access to testing of interacting smart contracts. We performed case studies by testing various well-known and real-world smart contracts such as tokens, escrow, or Congress, which is a simplified version of the DAO contract, Uniswap, and so on. And our benchmark shows that our testing framework can successfully discover many known vulnerabilities and bugs in these contracts. But of course, there are some tricky bits, specifically coming from the fact that certain generators cannot be derived automatically because producing completely random input is not so interesting. It can lead to too many discards. That's why users in some cases have to specify how to specify specialized generators. And let's talk about our last contributions. So we developed several examples of real-world smart contracts in concert, adding to our collections of smart contract implementations. And among these are Bodron voting, which is an interesting contract for voting, for computing public tally from private votes. And the interesting bit comes from that it's actually using some cryptographic primitives, which are based on finite field arithmetics. And we have verified this contract, functional correctness of this contract, and we are working on extracting this contract, including the high-performant cryptographic primitives. We also implement an escrow contract, which is a common contract in decentralized finance, and several standard token contracts, which are widely used to represent various assets and commonly used as library code for other contracts. In conclusion, to summarize, we demonstrated a practical use of metacoque erasure thanks to our extensions, and we implemented and verified an optimization of extracted code. And our development is sort of general enough. It's not only about smart contracts, but also can be seen as a step towards a verified extraction framework in COC. So we considered several extraction languages. Some of them are smart contracts, some of them are subsets of general purpose languages, including Elm and Rust. And we implemented a smart contract testing framework to aid the verification efforts. And moreover, we implemented several real-world smart contracts to test how our pipeline, to benchmark our pipeline from the implementation of smart contract all the way to producing executable code. And our development is available on GitHub. Other outcomes of our project include our optimization path was integrated to Certicoke, since the lambda box representation is one of the intermediate representations for Certicoke, and early optimizations at early stage might be useful. We also contributed to a development of Metacoque project as well. What are we going to do next? So we would like to add more optimization passes, and also handle this problem with inserting coercions for definitions that potentially won't type check in the result. in the target language. And also we have an idea how to fix this issue with applied box rule of a lambda box, which will allow to bring the semantics of lambda box closer to the semantics of target languages. And that was it. Thank you for your attention.